Hello everyone. In this video we will talk about electric potential. So electric potential is kind of closely related to potential energy and work. So let's start with work. So what is work done? And this is from physics 1 knowledge, right? So physics 1. So work done when an object that is feeling a force. So let's say that I have a block on which I'm applying a force in this direction. That's my force vector. If it moves by, let's say, a displacement dl vector, then the work done, okay, dw, that looks like F dot dl. Okay, this is a definition of work. Force, dot product of force and displacement, that gives you the work done. And we also know that the change in potential energy when this amount of dw amount of work is done, change in potential energy, let's call it PE, change in PE, that looks like du is equal to negative dw, which is equal to negative F dot dl. Okay, this is the idea of work and potential energy. So we're just going to use this idea, except now for electric charges, this force will come from the obvious force that we have been talking about so far, which is the Coulomb force. Okay. All right. So if I think about the Coulomb force, then I can simply write F is equal to a charge, the force on a charge multiplied by the amount of charge multiplied by the electric field gives the force on that charge. So if I have a electric field somewhere over here in a region that has electric field, I put a charge plus Q charge over here, then that charge will face this much amount of force. So now how much work will it do to if this charge under the effect of this force moves by a displacement dl, then that will be, so the work done will be equal to Q times E dot dl, and hence the change in potential energy associated with it would look like du equals negative Q times E dot dl. Okay, remember what electric field was. So electric field is the force on a unit positive charge, right? So in other words, E was equal to F divided by Q, right? So similarly, I can take this charge to the other side and write du over Q is equal to negative E dot dl. And this is where the idea of potential difference or potential itself comes from. So potential energy and potential are slightly different. So potential energy is the net amount of work done to move some charge Q when it's feeling a force E, force Q times E in an electric field E through a displacement dl, right? Potential, on the other hand, is the change in potential energy for a unit positive charge. In other words, what work do I have to do to move a unit positive charge by an amount dl in an electric field E? Okay, so that is dV, or so this is change in potential, and remember the other one was change in potential energy. Okay, that's where these two come from. Okay, so now these are tiny little changes. Those D's tell you L just means that this DL, we're going to take that limit that DL goes to 0 eventually, which means that if I wanted to find a finite change in potential, so if I wanted to find delta V, that would look like equal to negative. Now I have to add up all the dV's, so integral, so delta V is really integral over dV from some place where the potential is 0 to the full potential, and which will be equal to negative integral of E dot dl from the place where the potential was 0. So this is the place, let's say A, where such that V of A is equal to 0, and to B, where we are trying to find the potential. So VB is sort of what we are looking for. Okay, so now let's think about how to apply this to Coulomb. So Coulomb type force and Coulomb type potential. So first of all, so we will have, let's say I have an electric charge Q located at this point. We have already found the electric field due to this point charge at a distance r from the point charge. Okay, so at this place, the electric field vector is pointing like that. It is a vector, so it looks like E vector is a function of this. The radius vector looks like kq over r squared r hat. That's our electric field. Okay, now if you think about it, very, very far away, infinitely far away from this point charge, there's no interaction. So if I keep a unit positive charge very far away over here at infinity, then its potential must be zero. So V at infinity should probably be equal to zero. So now the question is, how much work do I have to do to bring a unit positive charge from the region where the potential is zero, which is at infinity, to this location at a distance r? That would be the potential associated with charge q. So in order to do that, we will write V of r. Remember, V of r is a scalar. Potential is a scalar quantity. Sometimes it's also referred to as a scalar potential. So V of r looks like that's equal to negative integral E dot dr. And since we have determined that V of V at infinity is zero, so we're going to start integrating from r equals infinity and bring it to r equals r. And just for the sake of properness, I'm going to use a prime on the integral variable. Okay, so now we can say that dr, this vector, the dr vector looks kind of like dr scalar multiplied by the unit vector r hat. Okay, this is the prime is just telling you that this is a variable that is different from r, but the unit vectors are still in the direction, in the radial direction. So the unit vector over at this point is pointing in that direction. The unit vector over here is again pointing in the radially outward direction with length 1, etc., etc. Right? Okay, and we know that the electric field is kq over r squared r hat, so let's plug that in. So we get V of r is equal to negative integral r equals infinity to r kq over r squared r hat dotted with dr prime r hat. Of course, since our variable is r prime, so we should probably make this an r prime. And the r hat dot r hat, this should give us 1. And so this simplifies and it becomes, and the integral variable is r prime from infinity to r, kq over r prime squared dr prime. And if I do this integral dr prime over r prime squared, that integral will become negative 1 over r. Okay, and when we plug in the limits, we will get kq divided by r prime between the limits infinity and r. So that's kq over r minus kq over infinity. And as you can see, this second term, because there is an infinity in the denominator, that's just 0. So V of r is equal to kq over r. So this is the potential due to a point charge. Potential due to a point charge. Okay? All right. What about its potential energy? Well, if I just have a point charge and I brought it from infinity to q, so originally when I had brought the first charge q over here, I didn't have to do any work because there were no charges around. So potential energy of a single p of a single point charge is 0, right? Let's try to plot this potential, V of r as a function of r. So kq over r, kq is a constant, which means that if I wanted to plot it, this is what it's going to look like. So if this is where the charge is located, it's going to look like that. As r goes to infinity, it goes to 0 on both sides. So this is my x-axis, let's say. So this is the negative direction of the x-axis. That's the positive direction of the x-axis. This is x equals 0. Okay, so if I were to write this in as a function of x, this potential, where we have said that at x equals 0 is where my charge is located, in the one-dimensional case, this would look like kq divided by magnitude of x. Okay, great. What happens if my charge was negative? What if this q is a negative value? So if the charge is negative, then you can see that the potential also will be negative. So this is particularly for a positive charge. Positive charge. Okay? If my charge itself is negative, this plot will also be negative, which means that this is going to be the form. Okay? This is for a negative charge. Negative charge. Okay, this is the plus x direction, and that's the negative x direction, right? And it's going to be exactly the same expression, except now that our q is a negative thing, if q is negative, then the overall thing will be negative. So let me give you an example. So if q is equal to 1 coulomb, then v of x looks like k multiplied by 1 coulomb divided by magnitude of x. Okay? And we know what k is. K is roughly 9 times 10 to the 9 Newton meter squared per coulomb squared. Okay, and the unit after you plug in everything, if the unit of x is in meters, then effectively what we will find is that the coulomb squared and the coulomb will cancel, meter squared and the meter will cancel. So eventually the final answer will be in Newton meter per coulomb, and that's also equal to volt. So 1 volt equals 1 Newton times 1 meter divided by 1 coulomb. Okay, great. What if my charge was q equals negative 1 coulomb? Then v of x would look like negative k times 1 coulomb over magnitude of x. So what happened there is I just plugged in q equals negative 1 coulomb, right? So so I could have written negative 1 coulomb inside, but then the negative would get pulled out, and I'd get k times 1 coulomb over magnitude of x. Okay? And again, the units idea is exactly the same. Let's now talk about what happens with 2-point charges. So let's say I have 2-point charges, one here and another over here. So let's say that the first point charge Q1 is located at x equals 0, and the second point charge Q2 is located at x equals a. They're both located along the same straight line, the x-axis, right? So this is my positive x-axis. So first we will talk about what is the potential of this system. So potential. So when I'm talking about potential, I'd have to pick a point where to find the potential. So let's pick this point. So this is a variable x. Okay, and as we change x, so as we move x along this line, we will find sort of a function, potential as a function of x. So that's our goal. So in order to find the potential x, we can use superposition principle again. Superposition principle, by the way, is extremely handy, right? So superposition principle simply tells us that we can add things. We can add potentials. So what we could do is we could find the potential at x due to each of the two charges Q1 and Q2, and then we can add those two potentials. So let's first find the potential at x due to charge Q1. So V1 of x. So this we have already done before, right? So this would look like k Q1 divided by the distance between x equals 0 and x equals x. And remember, we have to take the absolute value of this. And the reason why we have to take the absolute value is the potential doesn't know which direction you're going. Potential is a scalar, so it only knows the distance, the scalar distance, which means the magnitude of the distance, right? So v1x is equal to kq1 over x, magnitude of x. So that's my potential v1 due to charge q1. Okay, so this is due to q1. And now let's look at what happens for charge q2. So that's v2x. Then we will have kq2 divided by the distance between x and a, x equals a. So we'll have x minus a. So this is due to q2. All right, great. Okay. And now what's the net potential? Superposition tells us v of x has to be equal to v1x plus v2x. So that's going to be equal to kq1 over magnitude of x plus kq2 over magnitude of x minus a. And that's it. That's our potential function, right? This is it. Okay. So what does this function look like? So let's pick a few numbers. Let's plot this function as a function of x. But in order to plot this as a function of x, we need to make some simplifying assumptions. So let's say that our charge q1 is equal to 10 microcoulomb, and let's say Q2 is equal to 20 microcoulomb, we know that K is equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared. Okay, and then we will plot X as X in meters. So if X is in meters, then if I plug things into this equation, then we will have to know what is K times Q1. So K times Q1 is going to be equal to 9 times 10 to the 9 multiplied by 10. But 10 is a micro, so we have to put 10 times 10 to the negative 6. And now let's put in all the units. So Newton meter squared over Coulomb squared multiplied by Coulomb. So this Coulomb squared and Coulomb will cancel. That's our KQ1. But now if I put in KQ1 in Newton meter squared over Coulomb and then X in meters, then the potential V of X will show up. The unit for potential would be Newton meter squared per Coulomb, okay, divided by meter. So this meter will cancel with that. And we got Newton meter per Coulomb. But notice that this is just volt, okay? And let's sort of do this math over here. So we have KQ1 is equal to 9 times 10 to the 9 times 10 is 10 to the 10 times 10 to the negative 6, that's 10 to the 4. So 9 times 10 to the 4, okay? And if I wanted to write this a little more concisely, this is, by the way, in the numerator, right? So Newton meter squared per Coulomb is equal to Newton meter per Coulomb times meter. So this is volt times meter. Okay, what is KQ2? So KQ2 similarly is equal to 9 times 10 to the 9 multiplied by 20 times 10 to the negative 6 Newton meter squared per Coulomb, which is going to be equal to 18 times 10 to the 4 volt meter. Okay, let's simplify it a little bit. 10 to the 4 times volt. So let's take out the 10 to the 4. We will say 10 to the 3 volt is equal to a kilovolt. Okay, so then we get KQ1 is equal to 90 kilovolt multiplied by meter, and KQ2 is equal to 90 or 180 kilovolt times meter. Okay, now we are ready to plot this. So let's try to plot this in our favorite function plotter. So what we're going to write over here is going to look like V as a function of X, right? X. So that's defining a function. So this is going to be equal to KQ1 divided by magnitude of X. So we know what KQ1 is, which is 90 kilovolt per meter. So I'm not going to write all the units here. So 90 divided by magnitude of X, so absolute value of X. And remember, just to remind yourself, I would probably comment. So in a comment next to this, I would write V is in volt, V is in kilovolt if X is in meter, okay? All right, and now let's put in the second part of this, which is that plus KQ2 over X minus A, so plus KQ2, but that's 180, divided by absolute value of X minus A. So we should probably make an assumption for what A is, otherwise the computer wouldn't be able to do the calculation. So let's say A is equal to 1 meter. So let's put that in. So we'll say this A is equal to 1 meter. So if I plug that in over here, X minus 1, and so now we are ready with our function, right? So we are ready with our function, which means we can, the next step would be to plot. So plot V of X, and we can actually be generous and try to plot it from X equals negative 50 meters to 50 meters first. And we will, see what the plot looks like. This is what the plot looked like. Okay, let's go a little bit further. Can we go a little bit further and see what happens? Let's say 100 on this side and 100 on the other side. Okay, so that's interesting as well. Can we go any further? Does it make a difference? And looks like it's not making a lot of difference. It's just basically going smaller and smaller. Okay, what would have happened if one of our charges was negative? So let's now change the problem slightly and say that Q2 was a negative charge. So new scenario, Q2 is a negative charge. So if Q2 is a negative charge, KQ2 would be a negative quantity, right? And so in here, we'd have to put a negative value, right? So now you will see there's going to be something interesting that happens. Okay, so look, so at infinite plus or minus infinity, the function is still going to 0, but there's something interesting that's going on in the middle. So let's try to see what happens at the middle. And so in order to do that, we will reduce our range. And let's reduce our range to first -2 to +2. Let's see if we can get anything interesting in there. And yes, we immediately see that there are zeros over here, right, in that region, and then in this region. Okay, so we're gonna replot it in those two regions. So this is our plot, and let me just get rid of the old one. So that's gets rid of the old one. And now let's look at two different regions, 0 and 1, and then -2 and -1. Those are the two ranges where we are going to plot it. So -2 to -2 to -1. So that's what this looks like. And in fact, close to -1, it's getting to 0. So let's go a little bit further, -0.8. Okay, and you see now that at -1, it's a 0. Okay, so that's one example where the 0 was. Let's plot it again between 0 and 1, and here. There we go. So that's our 0, and that's our 0. So there are two non-trivial zeros of the potential. Okay, we have talked about the potential, but now let's briefly talk about the potential energy for the two-point system. So remember, for the first point charge, the potential energy was 0. For the second point charge, how much work did we have to do to bring that second point charge to this point over here? Well, that's going to be equal to really the potential due to the first point charge at x equals a. That's the potential, right? Multiplied by the second point charge, q2, which is equal to k q1 over a multiplied by q2, or that's the same as k q1 q2 divided by a. Okay, so that's the potential energy, right? This is potential energy. And let's try to see if we can figure out what the number, if we wanted to find a numerical value for it, what would that be? So this is, remember, this is the potential energy, U. So potential energy, U, looks like 9 times 10 to the 9 Newton meters squared per Coulomb squared, multiplied by the two charges. We had 10 microcoulomb and -20 microcoulomb. Let's use those numbers. 10 microcoulomb times -20 microcoulomb divided by A, just A is 1 meter, right? We put in A somewhere. We were assuming A equals 1 meter. So that's just this, 1 meter. Okay, so now the meter will cancel over there. Notice that there is a microcoulomb, so I can't immediately cancel the c squared with a mu c, right? So what we'd have to do is we would have to do 9 times 10 to the 9. There's an overall negative sign, so let me bring that out. 10 times 20 is 200, so multiplied by 200. And micro is a 10 to the -6, so there's 10 to the -6 times 10 to the -6, 10 to the -12 divided by 1. And now my leftover units is just Newton meter. The Coulomb square now cancels with the coulombs. Okay, so now this looks like 9 times 2 is 18, so -1800 times 10 to the 9 times 10 to the -12, that's 10 to the -3, so 10 to the -3 Newton meter. Remember, Newton meter is joule. Okay, so this looks like -1.8 joule. So that is the potential energy, right? So the potential energy looks like KQ1, Q2, K times Q1 times Q2 divided by the distance between the two charges, Q1 and Q2. And if I wanted to plug in some numbers, 10 microcoulomb, negative 20 microcoulomb gives me U equals negative 1.8 joule. Now remember that if this was positive, if I had a positive charge over there, this would also be positive, so the potential energy here would also be positive. So potential energy depends on what the configuration of the two charges is. So if both charges are negative, it's going to be positive. One of the charges is negative, the other one is positive, it's going to be negative. And if both charges are positive, then again, the potential energy is going to be positive.